Why should I trust the extrapolation of general relativity theory to the scales of cosmology? Bear in mind that the precision tests up until recently were limited to the scale of the solar system. Signals traveling between celestial bodies and reflected. Wonderful success for general relativity theory. But you're now proposing to extrapolate that theory from the scale of the solar system, 10 to the 13 centimeters, to the scale of the universe, 10 to the 28 centimeters, 15 orders of magnitude. On the face of it, would you trust a theory in an extrapolation of 15 orders of magnitude? Now, of course, we have a precedent. You extrapolate quantum physics from the scale of superconductors down to the Higgs. That's a long extrapolation too, and as far as we can tell, quantum mechanics works perfectly well. But then the question arises, well, why do you trust the extrapolation to large scales? Until recently, as I say, I was nervous about that, but with the success of the Marian acoustic oscillation signals seen in the microwave background radiation and in the galaxy distribution, I think we have an awful good case. Yes, general relativity is a good approximation to the scales of cosmology. But then the next question is, do you trust gravity? Do you trust quantum physics in an extrapolation that far? Why should I pay attention to theories of cosmology, of quantum cosmology? Why should I trust the physics of quantum mechanics extrapolated to that enormous scale? And if I don't trust it, then why do I pay much attention to the quantum, let's see, one of the great triumphs of inflation was to argue how we could understand the origin of near-scale invariant adiabatic space-time curvature fluctuations. Inflation gave us a wonderful account of how that could happen, but you remember it was never a prediction. You can adjust inflation to get all kinds of departures from homogeneity. The scale invariant Gaussian predictions are particularly simple, but that doesn't show that they're right. And by the same token, we were talking about Gaussian near-scale invariant perturbations before we had inflation, because it's the simplest possible thing you can think of. The assumption of scale invariant, near-scale invariance, adiabaticity, and so on, works very well, but does it really signal that it's from something like inflation? So that's my big question to you. Why should I trust these immense extrapolations in the absence of evidence? And let me, one other point that makes me uneasy. We remark, Alex, that even in internal inflation, the universe, eternal inflation can be eternal in the indefinite future, but it can't be eternal in the indefinite past. It doesn't bother me a bit, because I don't know why I should trust the extrapolation that far back in time. How do I know that inflation isn't simply a very good approximation to what happened back to that time, and leave it at that? Because remember, through most of my career was before inflation, we were doing good science. We had a cosmology which was absurd because it extrapolates back to a singularity. So we didn't pay attention to that part, just work with evolution from times like nucleosynthesis up to the present. We had a theory that was effective, incomplete, but after all of our theories are incomplete. So I don't know why I should be nervous about a theory like inflation that works so well and is incomplete, but everything else is incomplete. So, Bill?
Bill.
Yeah, I don't know. I can't add terribly much to what Jim has said. I mean, the scale invariant spectrum was postulated well before inflation. Again, that's the thing that you get if you don't have any particular scale that sets any particular scale which sets something within the theory, and nobody has any particularly good idea as to why in the world there should be a scale at these very, very at these very, very long wavelengths of the size of galaxies and so forth. So if there's no scale, then a scale invariant and spectrum is exactly what you expect. Also, the theory behind inflation, some scalar field looks like nothing that we have any knowledge of in the world. Scalar fields tend not to exist in particle physics, for example. Suddenly, what introduces this thing, it has adjustable parameters. Why are the density fluctuations or the CMB fluctuations down at 10 to the minus 5? Well, you have this little knob, and you twiddle the knob, and you get that value because you set it into the equations. Also, to a certain extent, inflation depends on those initial conditions, that you get a system big enough that inflation can smooth it out without all kinds of bad stuff happening in the process before it gets smoothed out by inflation. The theories of our initial conditions of the universe are pretty primitive and based on pretty primitive kinds of arguments. Another problem is, of course, that there have been a number of instances in which an observation was made of the way in which the universe was, like these B modes and so forth. B modes were detected. They're out there. People walked up to, Andre Linde and so forth, and he was extremely happy because he could explain that. Then they disappeared because that observation was just wrong. Well, as soon as they disappeared, oh yeah, I can explain that too. And once you have a theory that can explain anything, you no longer trust it to explain anything. So that again makes me feel uncomfortable. One of the big problems, of course, is that those, the two things, the scale invariant spectrum and that you both get, a smooth universe and one which has small fluctuations in it. We don't really have any other good theories that, people try. Theorists are a very inventive lot, but I think we don't have any explanations for that, if you will, other than inflation. And so it's best to stay with the wife that you've got beside you rather than searching for someone better if there's not any women anywhere else in the world. So, that's a problem. If one had alternative theories, then one could at least find ways of testing them against each other. So that's one of the counter-arguments to the kinds of arguments that I'm making. But I'm sure Slava Makhanov will have no answer. Will have no answer to any of these concerns.
I will answer to Jim and
That was a joke.
Okay, one should not read too much New York Times where some people say nonsense, yeah? Because, of course, you can take it. I know, but nevertheless, okay, there are some people who are also speaking about it. First of all, you can take Newtonian equations and can spoil them as you want. But good theory is a theory with a minimal number of parameters which makes prediction. And there was always these predictions. The problem is that between predictions were done and were done measurement passed too much time, and there was written too many nonsense papers. Because I wrote physics report where I had some section which I call garbage collection. Okay, so you take good theory and then you can spoil it and predict everything, yeah? But I can recall that in 2003, we were discussing with Lyman Page, does inflation predict scale invariant spectra? I told him for sure not. He wrote to me, if I would find spectral index 0.99 plus minus 0.01, would you give up on the theory? I thought, okay, I'm not married to this theory. I would throw oil on this thing. You see, because this kind of deviation of spectral index from n equal 1 is robust prediction, and moreover, it's the formula when we specify the rules of the game. When you are, look, when you claim that both accelerated expansion plus quantum fluctuations, okay, originated from one component, from the same component. When you start to play multi-parameter games, of course, you can get whatever you want. Yes?
Please. What you say is almost the entire truth, but not quite.
Why?
Remember, in single field inflation, I have a function, v of phi, which I may choose to get all sorts of results. That is a true statement, isn't it?
It's true statement up to the following extent. You see, there is an upper bound on the minimal deviation of the spectrum from scale invariant. Scale invariant spectrum you will never ever get if inflation should have graceful exit. Second thing, okay, when people started to speak about multiverse, how unavoidable consequence about this multiverse, especially if you merge it with this string landscape. So blah, blah, blah. First of all, you could actually make consistent model where you can avoid self-reproduction, forget about string theory. It didn't give anything good to cosmology, you see, besides of damage, as I would say. And the main point is that gravity doesn't care about particle physics. It will be the subject of my tomorrow talk. And I can confirm it that I never changed my mind in this sense. When there was last Planck result, I can tell you, Linda calls me and tells that, oh, people found big non-Gaussianities, FNL 400. And you are the only idiot who is going to speak about non-Gaussianities. I know the model. I thought I can also make hundreds of models like this one. But then if we will be able, okay, to make these models, it means that we learned nothing. You can explain everything with extra parameters, but you have to work always in the scheme with the minimal number of parameters. And if you remember, Jim, okay, this inflation was like Cinderella concerning predictions in 1980. 93, you were writing paper where omega was always not more than 0.3. Correct?
No.
Tell me, 93,
Inflation does not predict the initial conditions that fit the observations. As you say, you can get all kinds of predictions out of the inflation picture.
no
Just
way.
In single field inflation, just change the functional form via phi. Let it have bumps, wiggles. And of course, you can introduce two field inflation.
No, again, not the case. Because everything what we observe refers, if we speak in terms of the parameters, in fact, to one point in the potential and couple of derivatives, not more. You cannot really, even if you stand on the ears, you cannot change robust predictions that spectral index should be red.
Just don't see
Should
how
be
you can make
smaller
that
than one.
statement.
Huh?
I have v of phi. I change its functional form.
It doesn't matter. I tell you that I can take any V of phi, and there is a different approach also, besides of this V of phi, effective energy, how it's called, equation of state. Pressure and energy density. This is the things with which we have to operate there.
But why does an adjustment of V of phi not predict an adjustment of initial conditions?
Adjustment of V of phi you don't need. You have just to postulate that at earlier moment of time, there was, for instance, universe, closed universe of Planck scale, which was filled by dark energy, but decaying dark energy. So deviation of the equation of state from cosmological constant should increase. It's the only thing which you need to get robust predictions that spectra should be red. You see?
No.
Why?
I think I have said enough. Let others contribute.
Excuse me, who would like to comment? Paul.
Yeah, well, I find it very bizarre that I'm taking the microphone as a defender of inflation to some degree, but I mean, I don't think inflation provides an explanation for homogeneity because you'll need some homogeneity to get inflation. It's sort of, I don't think it provides much, it does very much on many other things, but I think it really does spectacularly well on explaining why there are deviations from homogeneity, you know, due to these fluctuations. Now, I'm talking about inflation as an idea. Every inflation model looks terrible. So there's no model of inflation particularly that I believe, although, you know, some of them, or one of them, I should say, may be right. I don't have but the idea that the origin of the deviations from homogeneity originates from quantum fluctuations in quantum fields in an accelerating phase in the very early universe. You know, although I've never otherwise liked inflation, I have to say is a really beautiful idea and I think quite compelling, and I think it goes, I'll hand the mic to you, Bill, to repair the damage I'm doing, but I think it also goes a fair way toward answering or is responsive to the question you were asking, why should we trust these extrapolations of theories, you know, down to, you know, these sort of, you know, grand unification timescales and densities of, you know, and so on. I think that's fairly absurd that we should be able to, but I think, you know, the fact that you can account in a beautiful way for the deviations from homogeneity with this explanation, I mean, gives me some reason to believe that maybe we can do that extrapolation. I mean, it's the other way around. A priori, I wouldn't have particularly believed that one could do this extrapolation, but I think this provides a bit of evidence that maybe one can.
Okay. I don't know. You know, your argument sounded like I have a theory that all men are 9 foot tall. It just so happens that every single man I've ever seen is only 6 foot tall. But I still believe that men are 9 foot tall.
I would say it's more like I have a theory that men are, you know, of order of magnitude meters tall. Every model, you know, the various models I have give 9 feet, 20 feet, 1 foot, you know, etc. And I can find one that gives the right answer. I don't particularly believe any of those models, but the general, I mean, the simple idea of in an accelerated phase of expansion, the quantum field fluctuations would give you the right, not only the right spectrum, which, if there's sort of no scale, maybe that's what you'd get, but, not a crazy, it doesn't predict that people should be a nanometer, or it doesn't predict people should be a Hubble radius. It predicts, something in the right ballpark. I mean, again, you have to tune that to get, if you really want to get, 10 to the minus 5, but it's not a crazy tuning that gives you that. So.
No, but I mean, you're making a huge assumption, and that is that, for example, as a fluctuation comes through the Planck scale, we have no theory of quantum gravity, so we cannot predict it. But as the fluctuation comes through the Planck scale, that it is basically roughly a vacuum, whatever that means, fluctuate. Wait, let me finish stating what I want to say. And if you take the theory backwards in time, you can start off with any, reasonable, if you will, 10 times bigger here, smaller there, whatever. Take that backwards in time according to the usual theory where you go forwards in time and you just take those and run that backwards in time. And what you find is that the universe simply has its origin, i.e. you get a singularity, which becomes highly convoluted in the past, which produces exactly that kind of a structure. Now, why in the world do you believe that the quantum state coming in through the Planck scale is going to be this nice vacuum kind of state? There is, again, the old argument that the problem is there's no causal mechanism that can produce this nice smooth state for you. So why isn't this model where I take my data, I just run it backwards in time, I get the singularities sitting there, a highly convoluted singularity sitting there. That's my theory of the universe. Well, I certainly wouldn't be happy with that. And yet that is, that accords perfectly with the theory of any inflationary theory that you might have or you might cook up.
Yeah, well, maybe I should let somebody else.
No, but can I ask you a particular question?
Hang on.
About this super-Planckian problem, yeah? First of all, you have the same thing when you calculate Hawking radiation. If you trace, when you calculate Hawking radiation, when you trace modes back, then, they become super-Planckian. But this is just method of calculation. You don't need to go to sub-Planckian scale. And as Bob said, there is, say, 5 orders of magnitude between Planckian scale and the scale when perturbations were generated. You could say that you took in some place, of course, because you are working at the energy scales which are 12 orders of magnitude below Planckian scale. And there is the gap between Planckian scale and inverse Hubble constant, where the space can be well approximated in Einstein elevator, and you have just Minkowski vacuum there.
Why do you have Minkowski? This is the origin
Very
of the
good.
universe.
If you are unhappy with Minkowski, you can take any state. The only condition that you should not excite too much to stop inflation. Inflation will get rid of all the garbage, but it cannot get rid of quantum fluctuation.
I'm talking about going backwards.
Backwards is the way of calculation. I told you, forget about tracing this particular mode in super-Planckian scale. Still, that expansion have stolen this thing, but then Mr. Heisenberg uncertainty relation will generate you in the appropriate scale.
No, it won't.
But
Heisenberg's uncertainty gives you delta x, delta p is greater than h bar,
but
not equal to h bar.
You agree that, for instance, if you take Minkowski space and describe in the Milne coordinate, then you also have to go to super-Planckian scale. But you know that the spectra is invariant. Mill coordinate description of Minkowski space. The same problem as you mentioned, okay? You have to trace your modes to
Certainly,
super-Planckian scale.
and in flat space, I know, in Minkowski space, I know that I have, for example, the Rindler vacuum, and I have the Minkowski, I have infinite number of Rindler vacua, and they all behave incredibly different from the Minkowski vacuum.
Very good. But nevertheless, okay, you know that the ground state is Minkowski vacuum.
But ground state is a global phenomenon. It's not that the local T mu nu doesn't commute with the global T mu nu.
Linear vacua is the observer-dependent notion. When you calculate your
With particle detectors, that's true.
Right, absolutely. But otherwise, you understand that people speak about de Sitter temperature. What kind of temperature is it? Is the things which is related with particular observer. Normal temperature
Agreed.
drops down inversely proportional.
But I mean,
scale.
in the case of Minkowski vacuum, well, I don't know why we're even an approximation of a Minkowski vacuum. Well, we're not.
Okay, so,
But anyway.
okay. So I think that, I mean, as this debate sort of showed, I feel that the best way to summarize it is a quote from Jim Peebles, right? And the quote here says that, well, inflation is not a theory. It's a framework on which to hang a fundamental theory. And I think that encapsulates this discussion extremely well. So, I mean, all the criticisms Bill is making, not all, but many of them, have to do with treating inflation as really something that is hard and, hardcore and, cannot be shifted or anything like that. If you think of it as just a general framework, as Bob was saying, I mean, general framework on which to hang a fundamental theory, then I think that it is very powerful. And now, the reason to take this as a framework is what people have said, and I think I agree with Slava that red tilt is not so, is a reasonably robust prediction. I won't say that every inflationary model will give red tilt, but it's just because the kinematics and dynamics, as the inflaton rolls down the potential, then the universe is expanding. If you just see what is happening to the Hubble parameter, that you're going to get a red tilt. So it's a fairly robust prediction of the whole thing. And so I think that we should, we can take this as kind of a framework, as sort of a hint, as a kind of a opening the window. I mean, it doesn't cover everything that is outside the window, but it's opening a window. And then one can ask these questions. Ask the question about potential. So take this as an opportunity that perhaps there is a fundamental way, perhaps there is a way to make sense of Starobinsky potential coming from some fundamental theory of gravity. And then, so people could work on it. I mean, of course, one can easily get it from fundamental theory of gravity, the problems of scale. Namely, the coupling constant is not Planck scale, but it's depending on how you write it, it is either 6 orders of magnitude larger or smaller, and then how do you explain this? But these are challenges. So to me, inflation is an opportunity. It has opened some windows which actually, focusing our efforts a little bit. And then the same thing about the initial conditions. Yeah, so you're right. I mean, the Bunch-Davies vacuum seems pretty ad hoc because it's in the middle of the inflation. It's in the middle of the evolution of the universe, if you believe in Big Bang, or if you think that singularity is resolved, then still it is in the middle. And we need better criteria to sort of find better principles, like Penrose's principle of, the wild curvature hypothesis is a classical one, so we have to take it to quantum level somehow. So to me, inflation is providing all these, little flashes of directions in which we could go. And I think that is very, very nice.
No, I have sympathy for what you're saying. My problem is that when one is looking at it for explanations for something, a wrong explanation can lead you astray for centuries at a time.
But so can sitting on the wall.
you have the ether theory of light, right? And people poured huge amounts of effort in trying to make the ether theory work, and even extending it so that it could explain atoms. I mean, it's a wonderful theory, right? That if you have these knots, etc., in the ether or in the ether flow and so forth, that maybe you could explain the existence of atoms and so forth. Was a fantastic insight, and gave exactly the kind of framework that you're talking about. But it was something that wasted everybody's time instead of producing what Einstein, this young whippersnapper from wherever it was, Ulm, produced it as an explanation, which came totally out of left field. So my problem is that a bad explanation can be an impediment to finding the right one. It's better to leave oneself in limbo and say one doesn't understand and that one is looking for the answer rather than latching on to a bad answer.
I disagree, because it's a competition, right? I mean, either you'll...
Yes.
Yeah, so it's a competition. So sitting on the wall can also, for centuries, can also hindrance to the to progress. What is important is that there should be competition of ideas. One should not have just one thing here, everybody just doing inflation and nothing else. That I completely agree with. Alternatives are great. For example, this is not an alternative, but one of the good things that have happened is that particle physics people are taking Higgs particle. I first thought, come on, it's impossible. Taking Higgs as a possible inflaton model, right? And they have done incredibly detailed work on it. Now, I'm not saying that therefore I'm completely happy with it, but there is progress. There are new ideas. And you are giving this example of Kelvin and Maxwell talking about knots in ether as being atoms that I was mentioning in my talk. Yeah, but out of that knot theory, that is how knot theory first came, right? So there are also unexpected bonuses that can arise.
Thanks. Douglas.
Yeah, I just want to interject a different point of view. So most theorists have a lot of fun talking about cosmology and the whole universe and so on, but most progress is made empirically. So most of what we learned about cosmology has come from data in the last few decades. So we've learned a bunch of stuff about something that could be inflation or something else. And there's a next step, which is to try to probe the B modes. So unlike what Bill said, there is a sort of natural prediction, which is at the level of maybe 10 to the minus 2. So you would like an experiment that can measure to 10 to the minus 3 for R. And I don't know how to assess how many models or something, but a large fraction of people's currently favored models would either be confirmed or ruled out if you can get to the R of the 10 to the minus 3 level. So there's a very clear target for the next generation of experiments. So that we're in very good shape there, and we'll either learn something or we won't. So in particular, LightBird in space and the CMB stage 4 experiment on the ground will reach about the 10 to the minus 3 level, and we'll learn whether some of these large field excursion inflationary models are correct or not. This is very different than the dark energy landscape that we currently have, where W looks like -1. There's thousands and thousands of papers on different ideas, but there's no target for how big 1 plus W is. There's just no target at all. So right now we're aiming for 1% or something. We have no idea whether it should be 10 to the minus 3 or 7 or 20. But for R, there's a very clear target for something like half the current popular models. I don't know how to assess that. But it's a real target, and people are working really hard to get to there. And we'll either learn something new that it's like inflation or something else. But there's some real optimism that we will learn something interesting in the next decade.
Let me try to reformulate the things a little bit. Forget about inflation. Think about alternative. About alternatives, okay, about which Steinhardt was going to talk tomorrow. But do you have any alternative at present to the origin of the structure from quantum fluctuations? No. Very good. So at least at this point we are settled. Second thing, we see inflation today, right? It's accelerated universe. It's useless inflation. But the question is why you could not use it for some kind of good purposes to amplify quantum fluctuations. Okay, maybe God gave us indication to think in this direction. If you prefer to think about contracting or bouncing universe, it's your right? But there is no alternative to quantum fluctuations, and it's much more important than the stage of accelerated expansion. You see, it's exponent HT, not big deal, we see it even today. But quantum fluctuations means merging gravity with quantum mechanics, you see, precisely, and then actually experimental verifications. If you want to say, because data are unbelievable, it's not just one curve. So polarization, for instance, I can ask, Jim, okay, should we believe also in our universe extrapolating it to the time of nucleosynthesis?
I'm very uncomfortable about the word belief.
Believe is the wrong word for science. Can we be sure about
How
extrapolation?
confident can we be? How much money would you place on a particular prediction of a theory?
If
It's a judgment call, of course, but yet, although all of our physics is incomplete, we have a lot of confidence in Maxwell's equations because we've had endless experience with them. We have a lot of confidence in quantum physics, although not extrapolated to such immense scales, so I feel a little nervous.
Very good. But okay, I don't have too much money to put it, on it. But okay, we could speak in a different term. But you see, for instance, deuterium, which Max Pittini measured, I mean, the abundance of deuterium, which has nothing to do with CMB, it's in precise agreement with determination of the baryon density using CMB, although they have nothing to do with each other. Second thing.
We all know all that stuff.
Yeah.
We have a lot of reason to trust the initial conditions of lambda CDM.
Yeah.
But where did they come from? I still object to the word predict, because you didn't predict, you chose a simple case.
No, it was the result of calculation. You understand that? Okay, when we were doing this calculation, I was not happy because I didn't get scale invariant spectra, okay? It was always deviating. You see, at this time I didn't know what is the reason for that. But you understand that actually when WMAP got the first indication that it's less than 1, Lyman told me that his hairs stand up. You see, it's non-trivial number, it's not 1. It's 0.96. You see what is measured at the level of 8 sigma. So I can give my hand in this case, not money, but okay.
I only object to the word inflation, prediction. But I'd love to hear some more points of view.
I have one. Hello? Yeah, sorry, I wanted to interject an alternative point of view. Actually, Jim asked me to ask Alex Vilenkin whether he had anything to say, and Alex told me to say that he agreed with Jim. So, or that, I beg your pardon, that you had no problem with what Jim was saying. That was what you told me.
Jim said that
Hang on.
Okay, basically Jim said that he is not very worried by the fact that we cannot extrapolate inflation all the way to past infinity, that the theory is incomplete in that regard. And I think what I was saying is that this is a fact of life, that inflationary scenarios must have a beginning. And if you don't worry about that, that's fine. But there are not no simple modifications of the scenarios. For example, if you want to avoid past incompleteness, you can consider a scenario where the universe starts being infinitely large, then contracts, and bounces and re-expands. This kind of scenario will be fine. So, to me, there is a problem with initial conditions because starting with an infinite universe, which is very slowly contracting, or infinitely slowly contracting, is a somewhat, I would say, unconvincing starting point. But if you don't worry about that, I have no problem with that. That's a value judgment.
But you can create universe from nothing, as you write.
I can create from nothing, yes, but that's a beginning.
Yes, that's okay. But what is wrong about beginning?
Okay, so Jim asked for some alternative points of view, so I'm going to try and throw some stuff in here. Just two remarks in the form of questions. First of all, as I understand it, one of the objections that's being made to the scenario that Sasha's advocating is that in the regime where we do believe general relativity, it's awfully simple, and there's no obvious explanation for why. And we know that the generic behavior of Einstein's equations, in fact, is extraordinarily complicated. And, I mean, one might ask why you don't see BLK behavior, for example. So that seems to me to be one of the points at issue, and it's largely based, I suppose, on a, shall I dare to use the word faith, about whether or not the extremely simple solutions should arise when one expects, in general, very complicated ones. And the second comment I have to make, so this was in the form of a question, I guess I'm going to get comments from people who really know this. One of the things that we talked about this morning was the question of whether or not you could extrapolate quantum mechanics beyond actually very small scales. And as I explained and yesterday, and Birgitta explained this morning, we have no evidence whatsoever that quantum mechanics works so far above a scale of about 10 to the 4 atoms. When one talks about superconductors and superfluids, it was explained very clearly a long time ago that actually doesn't involve the kind of macroscopicity that is defined by the measure that Birgitta was talking about, above a level of about 2 particles. So the extrapolation is much larger than what you were saying. It's basically from 10 to the 4 particles to however many particles and other degrees of freedom you want to put in the universe. So let's say of order 10 to the 90. Okay, that's an awfully big extrapolation. So my questions here are about, first of all, the extraordinary simplicity of the solutions that you're asking us to have faith in. And secondly, the unbelievable extrapolation of quantum mechanics to large scales.
The scales were small when quantum mechanics was relevant, you see.
Can quantify, I mean, it would be very interesting. It would be very interesting to work out the numbers here, but we're talking about energy densities of order the Planck energy density. Okay, but that's still over 10 to the power 100 joules per cubic meter.
I understand, but okay, if it works, then it works.
Okay. But we don't have any evidence for that working at that level. What?
That, okay, inflation, or what's so-called predictions of quantum fluctuations, is better to say because people don't like the word inflation for some reason, but quantum fluctuation, quantum origin of the universe structure, was ready to fail in many substances. For instance, the last test it passed when there was release on non-Gaussianities of F and L in Planck experiment, because before that people spreaded rumor that F and L is 400. Of course, immediately appeared thousands of people who explain this 400, okay? A lot of summer school were planned, as I would say. But the most amazing thing is that there was 400, but this 400 became 3 because people took into account microlensing. You see, it's actually so unbelievable proof of general relativity that it's just fantastic.
I'm not asking about whether general relativity works. I'm asking about whether quantum mechanics works.
Quantum mechanics works perfectly well because actually there is no reason, for instance, for quantum field, not to be quantized in linearized approximation. And there is spectral index, which involves, by the way, the ratio of galactic scale to the typical scale of CMB. This 0.04 deviation from scale of variance is not coming from nowhere. You see, it has particular reason. Formula involves gravitational constant and Planck constant. You see? Yes.
I feel I feel the need for a new topic. What do you say, as Philip just remarked, it is quite remarkable that the universe is so close to homogeneous. In the anthropic principle, this follows because if we lived in a universe that was chaotic, we would not have a solar system that can last for 10 to the 10th years. What do you think of that explanation?
Me?
You.
Okay.
And then others.
I guess my feeling about that has always been the following. When you ask, what is the probability that the universe should behave in such and such a way, you have to also ask, what are the alternatives? So you have to know something about the class of all possible universes. And most of the debate of this topic doesn't ask that question. It says, supposing we change the parameters just a little bit away from what they are. Well, anyone who's thought about the probability of complicated problems knows that that probability will vary in complicated ways with changes of parameters. Now, locally, you may find that you're at a maximum. But if you're dealing with, let's say, 10 to the power 500 possible universes, you expect an enormous number of maxima and minima, and you can tell nothing whatsoever about what the universe might look like anywhere else in this parameter space by looking at what happens when you fiddle with parameters around what you've got. So in other words, my feeling is that these arguments about the anthropic principle are basically pretending that they know what the probability measure is.
I am no fan of the anthropic principle, but yet it has a thread of truth to it. After all, we do live in a universe that is well so suited for the long time of evolution that we require to be here. But I'd love to hear some more opinions about this or anything else. Alex.
Yeah, take it through.
Well, I agree, since we don't know much about the fundamental theory of nature, it's hard to calculate prior probabilities for many of these different parameters that we may want to explain anthropically. But there are cases which appear to be rather clear. For example, take the cosmological constant. Right? The cosmological constant, if you ask what is the range of variation of cosmological constant that you can expect, you might expect some grand unification range, a Planck range. So it ranges from plus Planck to the fourth to minus Planck to the fourth. Now, and what is the range that possibly allows for the existence of life or complex structures? And this range is extremely tiny, at least if you think of life of the kind we have here. It's hundreds of orders of magnitudes smaller than the total range. So what is the probability, prior probability for that? It's about constant. Any function that you draw that varies in this huge range, and you ask what is the behavior of this function in this tiny range, which is not very special by any, right, for any reason. So prior probability for cosmological constant, I think, is very naturally flat in the range where we can, where it matters. And let me give you a couple more examples. If you take, for example, the sum of neutrino masses, also, they have no effect on the origin of life, probably, right? And again, you can expect, what is the range of these masses? Should be about Higgs or about, I don't know, maybe proton mass, but we know that if you change the neutrino masses, pretty narrow range, they mess up the structure formation. Once again, I think in that case, you can have a well-motivated distribution. And the final example I want to give is in the case of axions. I think one can pretty convincingly calculate the probability distribution, because axion is, just a simple field with a simple potential, which we sort of know, and that has been done, and people found pretty encouraging results for the ratio, say, of dark matter to baryonic matter using that model.
Yeah, well, I think, Jim, you said that the universe seems very well suited to life. I mean, that was sort of the question you were posing. I mean, I would put it as we appear to have evolved very well to be well suited to our universe. Now, I think if we had any idea of what it takes, what are the requirements for conscious life, maybe made with a totally different chemistry, maybe made without atoms, in some other completely different universe, I think then we might be in a position to make an anthropic argument of, but, if we just don't know if the universe were totally different, or maybe we're in a multiverse with very many different universes, and the strange creatures there are saying, well, the universe had to have this cosmological constant, and if the parameters are different, the quarks would have formed baryons, and you can't have that for life. I mean, you need the plasma. That's absolutely essential for life. I don't think I need to go on.
I couldn't agree more with what you just said.
Yeah, I certainly agree that there may be life totally different from what we have here. But if you imagine string theory landscape with, I don't know, in hundreds,
10 to the 500.
10 to the 500 vacua and so forth. There you will have all sorts of structures, but in particular there should be some slice of this parameter space which includes something like standard model, right? With different varying parameters. So let us consider this because we observe it.
But why does it have to be? What do you mean by a slice? Do you mean
No, I mean that.
hypersurface of dimension 10 to the 500 minus?
No, hypersurface of dimension 30.
Oh.
There are 30 parameters in the standard model, right? Out of.
Okay.
Okay, so I want to look just at that slice of the parameter space, and see what happens if I see variations of these constants that we know of, and find the probability distribution of that slice. I don't see anything wrong with that. Okay, well, I suggest to consider my comments at this point.
I very much like that comment. So let me ask the following question. Supposing I'm a very small animal on the surface of the Earth, and I'm on the top of a very small hill. And if I survey my immediate surroundings, I notice that I will roll downhill if I move very far in any of the two possible directions available to me. I can now ask, is there some slice through the topography of the Earth that will produce similar conditions? And there is indeed such a slice. But I simply cannot I cannot deduce from that that I'm at the highest point in the universe, which, by the way, is now the Earth's surface. Nor can I, in fact, say anything at all about what the rest of that Earth's surface looks like, made from my understanding of what happens if I make a very small change in my position. And actually, I'd like to add to what Bob said. The only reason that we have any understanding of our surroundings at all is because of a thousands of year history of scientific investigation. We are absolutely incapable of figuring out what a world would look like, just like that, if we changed the constants. We would have to go through the same several thousand years of work without the benefit of experiment and observation.
Alex, you said, I think, that the awkward vacuum energy density of quantum physics can be accounted for most reasonably by the anthropic argument. Does that mean you've given up the possibility of accounting for this vacuum density that's observed through physics that we can discover?
Well, I cannot give up on something that I don't know what it is, but I would say that despite the efforts of the best theoretical physicists for about 50 plus years, there are no convincing explanations of the observed cosmological constants other than the anthropic explanation.
That is true. Do we give up?
If tomorrow somebody comes up with a very convincing explanation, I'll be all for it. But at present, it's hard even to imagine where it is going to come from, because it seems that everything has been tried.
What do others say?
I would like to agree with Alex's point of view and argue against what Philip said about the possibility that there are higher peaks elsewhere. In some sense, that doesn't matter. It just matters that we know that our parameters are relatively special, and whether this is telling us something special about nature. For example, if there is only one ground state in your fundamental theory, then it has to predict all these parameters. If there's many ground states, then there are various possibilities, and the anthropic arguments come in. And so if you feel that the greatest problem in physics are these fine-tuning problems, the Higgs mass, the cosmological constant, the mass of the up quark, whatever, and you devote your whole career to it and you don't come up with a convincing explanation, you've been led astray. Because maybe those are somewhat random parameters and there is no convincing explanation for it. You should have spent your life doing something like looking for mechanisms for baryogenesis or something. These anthropic arguments are never going to be total proofs, but there are motivations for what types of theories to look for. Should you look for a theory that, should you make the unscientific assumption that the only possible theories are ones that have unique ground states? Or are you allowed to look in the class of theories that has multiple ground states? If you're looking at one class, the anthropic arguments come in. If you're looking at another, you have to come up with direct mechanisms to predict some of these funny anthropic coincidences.
Hi.
Oh, sorry, go ahead, please.
Yeah, Jim handed me this as though I would help somehow. For me, if an anthropic principle discussion lasts more than a couple sentences, it marks the edge of where we can play a real constructive role as scientists. So, you know, echoing Douglas a bit, we've made enormous progress in quantitative measurements of this kind of almost scale invariant expanding thing we live in. I think those measurements are driven a lot by theory, so Douglas and I maybe slightly disagree, but the measurements are a key bit. And for me, for sure, I mean, even if you say you know there was inflation, as Alex said, there must be something before it to trigger the thing that we, so it's easy to point to pick questions we don't yet have answers for. And it's nice to keep aware of those. But the thing we can do, you know, within my lifetime is precise measurements and careful calculations of the things we do understand and compare them to each other and see if, you know, no, completely, don't give up. But when you come to this, the only thing I can talk about here is anthropic, pull back a half a step and measure the things that you can make progress on, of which there really are a lot.
Yeah, I have just one question. Does the fact that the magnitude of the cosmological constant was actually predicted by Steven Weinberg, and at the time, anybody who would say that, if you're not Steven Weinberg, would be laughed out of the room. For example, Joe Polchinski said that he will quit physics if that value of the cosmological constant was ever actually discovered. And in fact, nevertheless, observations confirmed the prediction. So does this, do you think this validates, at least to some degree, the anthropic principle?
Sorry, in what sense was it a prediction?
In the sense that Weinberg estimated the range of values that are consistent with the existence of life. And then he said, if indeed the cosmological constant is, and the the values which are, the range of possible values is much wider, he said, if indeed we observe a small cosmological constant due to anthropic constraints, there is no reason for it to be any smaller than these constraints require. And that was, later on, this argument was refined, and people made a better prediction, closer to, because Weinberg had one order of magnitude off. But that was the gist of the argument.
Just to reply to that and make things a little clearer, I think this Weinberg thing is way oversold.
Yes, I agree.
So what Steven Weinberg's paper did was basically put an upper limit on lambda and say if lambda is too big, then it's hard for structure to form. But at the time that he wrote his paper, physical cosmologists were arguing about variants of standard cold dark matter models and so on. And there were people that favored open models and people that favored lambda models, and they both fit the data perfectly well at that time. So there was no empirical argument to favor lambda over open models. So the only argument really was an upper limit to lambda, and not a prediction of the value of lambda. So lambda equals 0 was perfectly consistent with everything that Weinberg said in his paper at that. I forget exactly what year that was.
Wait. Nobody
has a
says
different memory.
nobody says that lambda equal to 0 is inconsistent with anything. Of course, it is consistent. But Weinberg said that if lambda is a parameter that varies between different parts of the universe, then we expect its range of variation to be huge, based on particle physics. And in that case, if what we observe here is due to anthropic constraints, this upper limit that you are referring to, then it's very unlikely that lambda is even smaller than that. So if your lambda is limited by some range, you expect the actual value to be somewhere comparable to the boundary of that range, not much smaller. Much smaller values are constrained more than necessary, so it's much smaller probability to live in a region like that. And Weinberg actually stated that in his paper, not in his first Fitzgerald letter, but in a paper he published
in the Reviews of Modern Physics paper. I think
Yeah.
he did argue and anticipate a non-zero cosmological constant.
Yeah.
Oh, sorry, somebody over here.
So the cosmological constant is recently actually we are right now in this conference want to come up with a grand unification theory. Basically, is to follow Einstein's brilliant idea to come up with a fundamental principle and then derive the formula that can, quantum physics, general relativity, and all the structures can come out of it. So how can we do that? And the key is to find that fundamental principle. And so recently we did some work on this, and we proposed that holographic principle as a fundamental principle. And then we derived, using actually a very simple thing, find that space and time, there's a minimum space-time, the uncertainty principle between space and time. And we derived the holographic action, which is basically holographic action calculates the information that is can be encoded on the hologram. And then we find that our universe is also quantum physics, particle physics, and general relativity is just a projection out of that hologram. And then from this hologram action, we actually can calculate the cosmological constant consistent with current experiment. So the anthropology principle don't have to be, the only way to derive the cosmological constant. And I truly believe we can find the grand unification theory. And and also actually our work really shows that, you can, even from the holographic action, you can see how the dark matter and dark energy come out, and how the black hole's entropy comes out, and and also the large hierarchy between electric, weak electric scale and the Planck scale, how that hierarchy can be dynamically generated, how why we live in a four-dimensional space-time, and you can, all these kind of things in the future, the grand unification theory should be able to derive it, and also can maybe even to understand why electric charge, is that value, and what's the relationship between, the gravity constant and also the charge. Two of them actually, they can also, that relationship can be also derived from the future theory. So this is a very, we're at this breakthrough point. This is exciting experiment coming out. And also the theory really we need to look into some fundamental principles and do this very beautiful physics.